Today in the physics session, we'll be discussing the gravitation chapter. So gravitation is one of the important chapters in the main topic, basically. So every year we can expect one question from this particular chapter. So these are the very important topics that are being covered or are being asked in the previous mains examination. One is the Kepler's laws, and the second one is an acceleration due to gravity, and variation of the acceleration due to gravity with latitudes and all these things, geostationary satellites and polar satellites. So these are the important chapters. Along with this one, I'll also discuss some of the important formulas and the relations in this particular gravitation, please. So coming to the Kepler's laws, there are the three laws. You people know that particular thing. What is your first law of the Kepler's is? So the planets or then revolve round the sun in an elliptical orbit with sun at its one of its foci. Okay, they'll be moving in an elliptical orbit like this with sun at one of its foci. So this is your semi-major axis and sorry, minor axis, and this will be your major axis. So this is at the one of the focus over here. So these are the first thing is there. So coming to your what is this is called as a law of orbits. First law is called as an all planets. So what is that one is first one is all planets move in elliptical orbit. In in elliptical orbit. In elliptical orbit. Okay. So with sun at its one of its foci, or this point is called as a one focus. It will have the two focuses, obviously. So now coming to your second law. What is the second law? So this second law is going to be the very, very important one. So that all the planets cover equal areas in equal intervals of time. So what's going to be the condition, sir? All the planets, they cover equal areas, equal area in equal interval of time. Okay. So this is the one of the major important thing. So what is this particular thing means? Suppose there is a planet over here. If it is covering the distance from some A to B here, from A to B, in a time interval of some delta t, it will cover this area will be the same in the same time interval delta t from C to D. So this area covered and this area covered, both of them will be same. Okay. So if you consider this particular thing as your area, okay, fine. Now this is the smallest element from A to B in a small interval of the time. So I'll redraw it again here. So this is your point B. Let me take this is your point A. So it's a very, very small interval of the time. So B and this is A covering an angle called as an theta in a time interval of the delta t from this particular point. So since delta t is very small and your AB is also very small, or AB will also tending towards the zero. So that means an infinitesimally it's a very, very small one. So if it is a very small thing, then you can consider that as an almost triangle. So from the triangle that is O, A, and B in this case, you can write the area of the triangle is equal to half. Base is I'm taking it as an OA. Since AB is very small, OA and OB will be almost same, and that will be equal to some radius R if I take it. OA, that is base, into height is AB. That is nothing but the length of the arc. So from the formula of length of arc, AB can be written as an length of arc is equal to radius into theta. So when I substitute all these values, half into OA can be written as an, that is R into AB is R into theta. So which is equal to the half theta into R square. This is your area. Okay. So now from this one, if I differentiate this, that is area is changing with respect to the time. So differentiate. So differentiate this one with respect to time. Then it will be the dA by dt is equal to. So since radius is constant over there, then it will be the half into r square into d theta by dt, that is change in the angle with respect to the time. So change in the angle with respect to the time, rate of change of angle is nothing but called as an omega, that is angular frequency or angular velocity. So here it will be the angular frequency, then dA by dt is called as your half omega r square. So this is called your dA by dt, and your dA by dt is called as your aerial velocity. Aerial velocity. Okay. So this is the one. If I multiply and divide this equation with the mass, then it will be the m r square into omega by, that will be the 2m. I'm multiplying and dividing with the mass. M r omega square can be written as a moment of inertia I into m by 2m, which is equal to the L by 2m. L is called as your angular momentum, and this is, and m is the mass. Here I is called as a moment of inertia. So on this concept, you will be getting the sums in the previous sessions also. We have got some sums on this particular concept. They will be directly asking you the formula of this one, or the aerial velocity formula, which can be equal to the L by 2m. So please be careful of this one. It sweeps equal areas in equal intervals of the time, and for this condition, they will also satisfy the law of conservation of angular momentum. So for the same elliptical orbit, the planets, or they are going to be satisfying that condition. So law of conservation of angular momentum is there. This is your minor axis, major axis, and sun at the one of the foci here. So this distance is going to be the A, and this will be your A E, where E is called as an eccentricity. Sorry, this distance is going to be your A minus AE. You can take it as an directly. Sorry, I'll erase this one. 1 second. So that is your eccentricity. So this is your AE value. Okay. Hmm. This is AE is called as an eccentricity. Mathematically, you might be knowing that one. So this distance can be written as an A minus AE. If I take this distance as an R1 from the sun to the planet which is present over here, this will be the minimum distance, and this will be the maximum distance, that is R2 is equal to A plus AE. So this is your minimum, and this will be your maximum distance of, this is called as an perigee, and this is called as an apogee. So now, according to law of conservation of momentum at the point 1, and this is your point 2. So L1 is equal to L2. L1 is equal to L2 in the sense you can write it as an L1 is m into distance is r1, is moment velocity. Angular momentum is nothing but an linear momentum into distance. So m1 v1 r1 is equal to m v2 r2. So mass is same for the same planet. So V1 by V2 is equal to, that is R2 by R1. That is, if the distance is maximum A plus AE and minimum distance A minus AE, then if the distance is maximum, then velocity will be the minimum. Okay, so and if the distance is minimum, then the velocity will be your maximum. This also another concept that can be asked. This can be, if I cancel the a on the numerator and denominator, it will be 1 plus e, and this will be the 1 minus e. Okay, excuse me. So this is the one of the most important thing, please. A relation regarding the Kepler's second law. And now coming to the Kepler's third law. So this particular thing, whatever it may be, the planet which is revolving around the sun over here. So you can solve that particular thing, is that is the time period of the revolution is going the square of the time period of the revolution, which is your third law of the Kepler's. Square of the time period of the revolution is proportional to the cube of the distance from that particular thing. Okay, so that means t square is proportional to the radius, that is r cube. If it is a circular orbit, then your a value and b value, that is the semi major axis distance and semi minor axis distance, will be same. That is, in case of circle, then r is equal to the nothing but the radius, or else in case of ellipse, in the case of ellipse, then r should be equal to the a, that is your semi major axis. Okay, then in that situation you should be writing t square is proportional to the a cube. So please be careful whether you are applying this relation for the elliptical orbits or circular orbits. So these are your three Kepler's laws. The next one is the angular momentum of a planet. The question is, this is the previous question itself. The angular momentum of the planet of mass m moving around the sun in an elliptical orbit is L. So angular momentum, he has taken it as an L. The magnitude of the aerial velocity. That means he is asking what's a dA by dt is how much? What is dA by dt is L by 2m. That's this we have just now derived here. Okay, so this is the relation L by 2m. So this is the one we have derived. So this is the previous question as it is. You have got that particular thing. So your option will be the D. So now coming to the acceleration due to gravity. What is this acceleration due to gravity? It is the acceleration with which the body is being pulled by the earth. Okay, now if I write the equation, if according to the Newton's formula, the force can be written as an G capital M into small m by r square for an object close to the surface of the earth, and that will be equal to your mg. So your acceleration due to gravity, that is g, is equal to gm by r square. So since it's an acceleration, obviously it will have the units of the meter per second square, or in this situation the acceleration due to gravity is numerically equal to the e, which is nothing but an gravitational field intensity. Gravitational field intensity. Okay, so these are the both of them are the similar kind of same thing. Numerically, they are same. Okay, you say the force F is equal to mass into gravitational field intensity, or intensity is defined as a gravitational force per unit mass. This is the same thing, basically. You'll be getting the same sort of an formula for both the things. Now, coming to the this we have derived, we have got the relationship between the acceleration due to gravity and the g. So we know that g is going to be varying. We know that g will be changing with respect to the different conditions. First one, acceleration due to gravity, g varies with altitude, Altitude in the nothing but an height only. So how does this particular g value will be changing with respect to the altitude here? So now let's see that one. If the on the surface the acceleration due to gravity is g m by r square. If you go to certain height above the surface of the earth like this, suppose this is the center of the earth, this is your radius r. From here I'm going to a point called as an p here, which is at a distance of h. Now at that point, what will be the value of the g? Let us take it as a g dash. G into capital M by that will be the R plus H whole square. So on comparing this one, G dash by G is equal to, so if you put down them in the ratio, that will be the R square by, which will be the R plus H whole square. This will be the generally used formula, please. Okay, if H is very less than R. For example, let me confine that particular value to you. If H value is somewhere around some 500 or 600 kilometers, if H is or confined up to, H is almost up to 500 kilometers thing. That means in front of the R is equal to 6,400 kilometers. Then it is almost 500 or 400 kilometers up to this one. You can consider H to be the very small value. Okay. So if H is very small in this case, then you have to go for the another relation. Or if H is a considerable value, if H is a considerable value, then use only this formula, please. Don't confuse yourself. If H is very small, then what we have to do? Then we can write it as an G dash by G is equal to. I am reciprocating them. This is R by R else. Let me take like this. H commonly I am writing it as a whole square and reverse this one. R plus H by this is R whole to the power of minus 2. So from this one G dash by G is equal to this is 1 plus H by R whole to the power of minus 2. So now we can apply the binomial theorem since H is very small. 1 plus X whole to the power of minus n situation this is there, and you can write this one as an on binomially first two terms 1 minus 2h by r, or your g dash is equal to g into 1 minus 2h by r. Strictly I'm saying this relation has to be used only if h is very less than r. Only in this situation please use it. Only in this situation please use this particular thing, sir. Okay na? Right. So next one, acceleration due to gravity, how it's going to be changing in the second phase. So acceleration due to gravity will be changing. That is, A is equal to the or G varies with uh, depth. G varies with depth. Okay, now this is another relation. So now you can write it as an G dash is equal to, or on the surface, you can go for the formula. I'm just changing the relation. G is equal to Gm by R square. This can be converted into the another form as G into this will be the 4 by 3 pi R cube volume into density. I'm writing that is rho. Mass is I'm writing, and this is your R square. Remove the common terms, please. Then G formula can also be written as an 4 by 3 pi rho G R. This is another important variation in the G formula. So in this case, you can say that G is proportional to the R. Since G is proportional to the R, now at certain depth of D, then G dash can be written as an 4 by 3 pi rho G into this can be written as an R minus D, since if you consider this to be the Earth's surface, Then from here to here, it is been reduced. You are coming to a distance of the d from the surface, this one, and the remaining distance will be the r minus d. Okay, so this is the situation, sir, please. This is the situation r minus d. Now when we divide this one, that is g dash by g is equal to 4 by 3 rho g, all those terms will be cancelled, r minus d by r. From this one, this is 1 minus d by r. From here, g dash is equal to g into this is 1 minus d by r. Okay, na? This is the condition. Right, sir? So now this is another important case, please. So this is how the g varies with respect to the depth. Okay. So next one, please. In another question on this base, the value of the acceleration due to gravity is g1 at a height of h is equal to r by 2 from the surface of the earth. It is then equal to the g1 at a depth of d. Then he is asking the ratio of, that means what he is telling, sir? He is telling that acceleration due to gravity at a certain height h is equal to g1. So since it is an r by 2, I am going for the generalized equation. So which is what, sir? R square conditions here, whatever I have written this one. So that will be equal to what? So this into r square by this is r plus h whole square. So since h is equal to r by 2, so your value will be g into r square by r plus r by 2 whole square. Solve it this one, then g is equal to g into r square by this is 3r square by 4, that is, or 4 by 3r square. I'm cancelling these two things, which is 4g by 3, right? This is the value. Now, this value is equal to the at a certain depth. That I'll take it as a GD is equal to G1. He has written GD formula is G into 1 minus D by R. But what is the value of the G1 we have got? 4g by 3 we have got. Remove the g. He is asking d by r is going to be how much? 1 minus d by r is equal to how much, sir? This is whole squares. So okay, this is whole square now, so this should be the 9. So I have written this one as a mistake. Okay, this should be the 9 over here, since it's under the square conditions, please. So now 1 minus this will be the 4 by 9. Now resolve them, then d by r is equal to 1 minus 4 by 9. That will come out to be the 5 by 9. So this should be your answer. Fine. So this is how the type of the sums. Now variation of the g with respect to the latitude. How the g varies with respect to the latitude, that comes with a huge derivation. I'm not going to that particular derivation. It's a time consuming one. I'll just explain briefly. Suppose if you take a mass here, then one of the force mg will be acting in this direction, and your centrifugal force mr omega square will be acting in this direction. The angle between them, if this is theta, then this will be the 180 minus theta. And solving this one, two forces, parallelogram law vectors you have to apply. On solving this one, variation with respect to the latitude. Latitude means what? The lines parallel to the equator are called as your latitudes. So G varies. How does it going to vary? G is equal to G minus R omega square cos square theta. That means as theta value, this is the theta value, sir. As theta value is going to be changing, this one, your G value is also changes. That means if theta is equal to, if theta is equal to 0, that means on equator, G on the equator is equal to, you're removing something from the G, that is G minus R omega square you are removing. Similarly, if theta is equal to 90 degrees, 90 degrees means at poles, this is the one, please. Okay. So this is at the poles, please. So on that sense, if it is the poles, then G on the poles is equal to This will be what can be a relation? G cos 0, cos 90 will be 0. So perfectly G, that means G at the poles is greater than the G at the equator. So based upon this relation only, we have got this one. So this is a very, very important thing you need to remember, sir. Please, this is a formula. A lot of questions might be asking on the weightlessness concept and all these things. That means if a body feels weightlessness, that is the weightlessness in the sense G dash is becoming 0. What does happen if G dash is going to become 0? Then G is equal to, that is R omega square. Suppose it is rotating such much fast at equator where theta is equal to your 0 degrees. So cos 0 is equal to 1. So I'm writing this one as a G is equal to omega square. Then what should be your angular velocity then? Omega square is equal to G by R, or from this one your omega is equal to root over G by R. G value is 9.8 and R is some 6,400 kilometers, that is into 10 to the power of 3 also. If I take this one, then you can solve this one as you'll be getting the omega value to be omega is equal to 1 by 800. This value you should remember, please, because in examination you cannot have all these calculations. So 1 by 8 value is, that is 0.125 into 10 to the power of minus 2. 1 by 8 value is 0.125, or this is 1.25 into 10 to the power of minus 4 radians per second. So this is the value you have to remember, please, because in the examination we cannot go on solving. It's going to be the time consuming or time wasting, time waste over there, please. And from this one, how many times the time period has to be increased? If I substitute this particular value, that is time t dash is equal, so t by omega dash, I have to write it. So if I write for the t by omega dash, then what will be the time period in the sense? This will be equal to the, when we substitute and solve this one, that is 2 pi by 1.25 into 10 to the power of minus 4, and substitute and solve this one. I'll get it as an 1.4 hours, please. I'll get it as an 1.4 hours. Okay. This is the situation, please. 1.4 hours we'll be getting. 1.4 hours, if you try to convert that into the minutes, then it will be somewhere around 84 minutes. It should be coming out. So this value also needs to be remembered. That means d dash is nothing but an 17 times faster than the t. So if the planet or the earth rotates 17 times faster than the than right now, then the person on the equator feels weightlessness and he flies off into the space. Okay, so this is how these values, please remember them. So you can see this, I think so fortunate we have got the same thing. So angular velocity of the spin. This is a previously asked question only, ma'am. So everybody increase such that the bodies at the equator start floating. Duration of the day would be approximately how much is going to duration of the day? Just now we have solved. It feels starts floating means what is the meaning of the starts floating? Feeling weightlessness. That means G dash is becoming 0. When the G dash will become 0, sir? When this time becomes 84 minutes. Okay, so as we have solved just now, so it's been easy for us if you remember these values. Remember this omega value, that is 1.25 into 10 power minus 4 radians per second, and time period has to be increased by 17 times. How do you get this one, sir? That means nothing but t dash is equal to initial time is 24 hours by the new time period is 1.4 hours. If I divide, almost this comes out to be your 17 times faster than your original thing, please. Okay, that is the ratio, please. Next one. So this is how you can solve them easily, please. So next type is called as your next instant, basically the geostationary satellites and the polar satellites. What do you mean by geostationary satellites? The satellites whose time period is equal to whose time period is equal to what, sir? Time period of Earth. Time period of Earth. So what is this time period of the Earth is? That is 24 hours. So that means are what is are the satellites which are revolving earlier was not used to be rotated for 24 hours? Definitely not. Okay. So the satellites which revolve close to the surface of the Earth will have the lesser time period than the Earth, and the satellites, for the geostationary satellites, you have to place the orb of satellites at a height of smaller is equal to radius of the Earth plus height. So this is from the center. I'm writing 442,400 kilometers, or from the surface of the Earth, or from the surface of Earth, it should be at a distance of 36,000 kilometers. When you place at that particular distance, then the time period of the satellite, okay, will be matched with the time period of Earth. Earlier, was these satellites are there? No. Small interesting thing I'll just tell you. Okay, so in earlier days, that means when we go somewhere around 1983. Okay, so most of your mothers and fathers just born just 10 years before that particular time period. What I am going for in 1983. 1983 is the period where the television has launched in India first time. Okay, so we could able to see the television in 1983 first time launch. So what's the new thing? So what's the specialty over there? At that time, till 1987 or 89, I remember till that time, we used to watch the television only from start in the at the starting. We used to watch it from some 6 to 7:30 only. Only 1.5 hour we used to watch the television. Why? Because the satellites sent by the India, that is the first primary satellites, INSAT 1A, INSAT 1B, they used to be there on the Indian surface for only that 1.5 hour. So in that 1.5 hour only, from the base station, that means from the telecast station, the signals will be sent to the satellite, and from their satellite, they are being received by your TV towers and the TV antennas. So we used to watch only that 1.5 hour. After that, gradually it has been extended to the some 5 to 9 or 10, and after that, some morning programs are also been added. Now, because these geostationary satellite, you can able to see the television for 24 hours. So that is the advantage of your geostationary satellite. That means if any satellite sent by the India, if it is a geostationary satellite, that satellite will revolve along with the Earth. That will be over on the on India only, continuously rotating all the time. It will be watching the India. So that is why you can able to get these particular channels or TV programs or cell program, whatever it may be, within time or 24 hours, please. Then what is this polar satellite, sir? So polar satellites are those satellites which will be close to the surface of the Earth, close to the surface of Earth. That means you have the radius of the Earth to be equal to the radius of the orbit of the satellite. That will be the 6,400 kilometers only. So these are the satellites which move close to the surface of the Earth are called as polar satellites. Okay. Hope you are clear with this one. Now, if we go for the geostationary satellite question, a geostationary satellite is a one which is orbiting around an arbitrary planet. Okay, something at a height of 11 times of its radius, which is a huge one. Basically, if it is 3,600 kilometers, that means 6 times of the radius, 11 times of the radius. Okay, now above the surface of the planet P. That means from the center of the planet, it should be from center, it should be 12 hour, no? From the surface, if it is 11 hour, from the center, it should be 12 hour. The time period of the another satellite in hours at a height of 2r from the surface P has a time period of 24 hours. So what is the time period of the other satellite, he is asking. So if it is a geostationary satellite, then time period of the geostationary satellite should be 24 hours. And the radius of the geostationary satellite is 12 hours. Okay, this is for the geo I'm writing. Now time period for the another satellite, let me take these values of the T1 and this value as R1. Time period of the secondary satellite, we need to one whose radius R2 is equal to. At a height of 3R means from the center it should be at a height of, sorry, 2R means from the center it should be at a height of 3R. Now apply the Kepler's third law, that is T1 by, can I go for the T2 whole square, where T square is proportional to the R cube, is equal to your R1 by R2 whole cube, that is, this is 24 by T2 is equal to R1 is 12R by, this is 3R, I can write it as a whole to the power of 3 by 2. RR we go, this goes for 4 times, that comes out to be the 24 by T2 is equal to 4. Can I write it as a 2 square whole to the power of 3 by 2? Cancel them. And this will be 2 cube. So that is T2 is equal to 24 by 2. Okay, so this is how you can solve this particular thing. Obviously, you should be getting it as an 3 hours. Okay, so now these are the very, very important things, ma'am. So hope you have understood. So you can use the more number of the sums. You can solve the more number of the sums from our RISE platform. Please use the code JJ10 to get the 10% reduction in your subscription fee, please. Now coming to the questions based on this one, please. Some other questions. Actually, you need to solve this one, but I'll go for this. So the gravitational field intensity, nothing but E he is still asking about, or G is nothing but the G. At A and C, this is the point which is inside and this is the point which is outside. This is the point which is outside. It is the point which is outside and are equal, uh, but less than at the point B. Why? Because B is on the surface. Y means B is on the surface, please. OA is to OB, he has given the X. That means this particular distance is X. And AB, this is nothing but the Y. But can I write the OB, which is the sum of OA plus AB as a radius, which can be written as an X plus Y? Just I'm keeping it aside. Now he is asking the value of the X. Gravitational field intensity at the A and at the C are equal. That means G at a height is equal to the G at the depth. What is the formula of this one is G into R square plus R plus H whole square. What is this 3200? Can I write it as an, since R is equal to 6400 kilometers, H is equal to R by 2. Can I write it? Because 6400 by 2 is nothing but your 3200 kilometers only. So I'll be substituting next. This is G into 1 minus depth D by R. What is the depth D is Y. R is X plus Y. We'll be replacing that particular thing. G first primarily will be removed. This is your R square. And this will be R plus R by H. This is 3R by 2. Sorry, whole square is equal to, this is 1 minus D by R. From here you can remove the R square term. So this is 4 by 9 is equal to 1 minus D by R. Just now we have solved the sum. D by R is equal to 5 by 9. Now substitute the D value. What is D, sir? Y by X plus Y is equal to 5 by 9. Can we reverse it? X plus Y by Y is equal to how much? 9 by 5. Split this one. That will be the X by Y plus 1 is equal to 9 by 5. So take the 1 to the other side, 9 minus 1, that will be x by y is equal to how much, sir? That will be the 4 by 5. So substitute r is equal to, you can get it. Okay, now r is equal to x plus y. You can replace the value, please, here. You need to find out the x value. I am substituting the y. So from this relation, y is equal to 5x by 4. X plus 5x by 4. This is equal to the r. Take down the LCM, please. 9x by 4. This is your r. From here, x is equal to 4r by 9. So go for the solving. Substitute the r value is equal to 4,900, 6,400. You can find your answer respectively, please. Okay. So that is an issue. Next one, please. So the time period of a satellite in a circular orbit of r is t. Circular orbit means from the center he is giving. Time period of the another satellite of the circular orbit of 9 are directly go for the Kepler's third law. T square is proportional to the r cube in the sense t by t2 whole square is equal to simply r by this is 9r whole cube. Cancel this one. So t by t2 is equal to 1 by 9 to the power of 3 by 2, which is 1 by 3 cube, that is 27. T2 is equal to 27 times of T1. Okay, so these type of the questions, please. Now this is another case, please. A sphere of mass m has a gravitational field at a point P is G1. Because of the entire sphere, it is G1. So G1 or gravitational field E1 or E total, I'm taking it this as an is equal to formula is Gm by distance small r square. So small r is nothing but here 3r from the center. So it will be the Gm by 3r whole square, which comes out to be the Gm by 9r square. This is the this value G1 means. Okay, fine. Now what he is doing is he's removing this particular region, sir. He's eliminating this, he is removing. Then he is asking what is the new value. So if we can go for E remove, I am going for this relationship. E removed is equal to E total, sorry, E total minus E removed. Don't worry, I'll change this one. This is E remaining. Yeah, E remaining is equal to total minus removed portion. So we have got the total with us. Now E remove. How do you find out the E removed? G into removed mass, that is m dash by its distance from the removed distance to the point P. What is this distance from the removed center to this one? Which is 3r minus r by 2. So that means 6r minus r, that is 5r by 2, or else 2.5 r, right? So this is the removed distance, which is r by 2. Now this will be a distance is small r square, which is I can go that 5r by 2 whole square. Now what is your m dash value? So for the total mass, if it is 4 by 3 pi capital R cube, then m dash on solving you should be getting it as an m by 8, since the radius of the removed portion is r by 2. If I substitute r by 2 here, 1 by 2 whole cube will be m by 8. Okay. So on substituting these values, g into this is m by 8 by 25 r square by 4. So now this goes for 2 times here. So this will be the gm by 2 into 25, that is 50 r square. Now put it in the final equation. E remaining is equal to E total minus E removed. So if I substitute here, that will be the G capital M by 9r square is equal to G, okay, he's asking the ratio. Sorry. Okay, then find it out. No problem. This is GM minus GM by 50 R square. This value he is naming it as an G. So subtract these two values. You'll be getting some answer. That value, after getting that value, put it in the G1 by G2 ratio. You'll be getting your corresponding answer. Okay, so this is the information, please. So due to the this one weight of the pole, you can go for this one weight of the pole at the 49 newtons. Weight at the equator, that means G at the pole is equal to the 9.8. So that means weight is equal to mass into 9.8. This is equal to the 49, and removing this one, you'll be getting the mass is equal to 5 kgs. So the value at the equator, weight at the equator should be less than 5 kgs because G is going to be the less in the given options. This is greater than 49. This is 49 equal to 49. This is also greater than 49. The only option that is left over is this one. So this should be your right option for the equator. Weight at the equator will be equal to this one. Got it? Next one. If the earth has non-rotational motion, weight of the person at the equator is W. Same sort of a thing. The speed of the earth would have to rotate about its axis so that the person feels that weight is going to be the 3/4 of the weight. That means he has asked your G dash is equal to 3 by 4th of the G, which is equal to the G minus R omega square. Only I'm writing since theta is equal to 0 degrees. So cos 0 is equal to 1 at the equator, now this one. So on solving this one, this will be the G by 4 is equal to R into omega square. He is asking omega is going to be how much? As already we have, I have solved this one. Omega will be equal to the 1 by 800 radians per second. You can multiply this one with the 1 by 4. That is 1 by 32. 1 by 32 is mostly, it should be the 0.63 because 1 by 32 value is 0.0625. Then it can be the this value, please. Okay.